Hi everyone. I'm going to discuss about applications of fuzzy logic in linear programming. Linear programming models. Since this discussion is about integration of the fuzzy logic and mathematical programming, especially linear programming, uh, I recommend you to study the operational research, special linear programming, as well as the fuzzy logic. And it is necessary to uh, learn about the base of these issues, especially fuzzy logic and linear programming models, and in their structures. And about the fuzzy logic, it is necessary to learn or to study the fuzzy systems, the fuzzy numbers, trapezoidal fuzzy numbers, triangular fuzzy numbers, the fuzzy relations, and the elementary principles of fuzzy. And also about the mathematical programming, especially linear programming, it is necessary to have information about the structure of these models. Okay, today I want to introduce the structure of mathematical programming, especially linear programming, and then I want to give you information about the applications of fuzzy logic in this programming model. In the first place, I must introduce the structure of linear programming. Okay, we can review the structure of linear programming. The linear programming is one of the uh, model of mathematical programming, so that this is all equations of this model is based off decision variables, the first degree decision variables. All equations in this model. The linear programming is composed of the objective function maximum or minimum. The objective function must be maximized in the discussion of optimization or minimized in this discussion, and it composed of z as objective function, single objective function in simpler structure, equals the equation, the expression, mathematical expression, comprised of c and x. C is the vector of coefficients in objective function, and x is the vector of decision variables. These decision variables are independent variables that the z or objective function is dependent of the x vector or decision variables. This maximum z equals cx subjected to many equations or inequalities, mathematical formulations. In this section, we call these inequalities or equations constraints. Constraints are figurated with these equations. For example, inequalities a multiply x is less than b. A is the technical coefficients in the constraints, and x, same as the decision variables in the objective functions that I said, and is less than the expression in the right hand side. What's the expression? This is the constant value. B is called the right hand side. And the third section of the linear programming is the sign of variables, decision variables. X, for example, is non-negative. This is positive and 0. Okay, this format introduces the structure of linear programming, a standard linear programming in the maximum format, and other format, standard format, is notated by minimum. Minimum z equals cx subjected to the more constraints, but constraint is notated by these expressions. Ax is greater than right hand side, and x vectors or decision variables are greater than 0, non-negative, or positive and 0. Okay, we want to use the fuzzy logic or fuzzy numbers, for example, trapezoidal fuzzy numbers or triangular fuzzy numbers in this structure, and then we must convert the fuzzy mathematical programming model or linear programming model to the crisp or deterministic structure of linear programming model. My purpose is to teach the ways that you apply the rules for making these models with fuzzy logic, not memorizing. There are many relationships and fuzzy relationships and crisp relationships, so that sometimes you are coerced to memorize these relationships and complexity. We are better to learn the rules, the important rules for converting the fuzzy structure to the crisp structure of linear programming model. Okay. In this section, I must explain about the plot. The plot that the membership function or membership degree, fuzzy membership degree, and value decision variables, for example, or objective functions, are notated in this plot. And this is very important for respecting the rules and making the fuzzy linear programming and then converting to the crisp linear programming model. In the first place, I'm going to explain the structure of maximization. There is the horizontal axis shows the, for example, fx, objective function, or z or cx in the linear programming model. And the vertical axis shows the membership degree. As I said, you need to have information about the structure and the principles of fuzzy and the elementary principle of fuzzy logic and systems and numbers. But you can notate the mu. Mu introduced the membership function, for example, z. Okay. And in this plot, we can figurate the maximum objective function so that with parallel line, excuse me, the sloping line from this point, for example, to this point, and then the parallel line with horizontal axis. And what does it mean? We call this point z uppercase L, z lower, the lower bound for objective function. And this point is called z upper, the upper bound for objective function, so that after upper, the membership degree equals to 1. The membership degree is difference from 0 to 1, as you see on the vertical axis. And the amount of z from zl to zu, and after that zu, introduce the value of objective function. The value of objective function and the maximum value or optimum value, global optimum value of objective function in the linear programming, for example, equals z upper, the optimum value, z star, z upper. After that, we can say there is a feasible value for z, so that we can receive to the optimum value. But we assume that the optimum value is localized in this point with notation of z upper. And we can accept some deviation or tolerance with the optimum objective value, okay, so that with defining the allowable deviation, and we can figurate the structure of fuzzy model. As you see, the deviation can be localized in this point, can be localized in this point, can be localized in this point. So receive to the z lower, and this cannot be less than lower of z, because the violation or the deviation is defined between ZL to ZU for maximization of Z in structure of fuzzy linear programming. And in the first place, we must write the membership function of this structure. Mu, the membership function of Z totally. Equals, as you see, when Z is less than lower of Z, the membership degree equals 0. Less than this point. And after upper Z or ZU, Z of U, is greater than equals same as ZU, you can see the membership degree equals 1. And this part determine the crisp situation of the objective function value. And between 2 points, between Z lower and Z upper, you can write the equation of this line from ZL to ZU. For example, this line with intersection of the parallel line with mu or membership function axis, you can see this point. This point is variable membership, and we can determine with this equation, fractional equation that you see. I will explain. Okay, if you divided this value to divided this value by 1, the 100% membership degree, you can determine the membership function. From variable z, so we can say that z minus lower of z or zl divided by total distance or interval and distance between ZL and ZU. This fraction equals to mu Z divided by 1, this part. Okay. So when Z is between ZL and ZU, the membership function of Z equals to the Z minus ZL divided by ZU minus ZL. So what is our purpose? What is our objective function in the structure of fuzzy linear programming? We must maximize this value, this variable. We call this variable lambda. And if we want to maximize this variable, we must define lambda is less than Z minus ZL divided by ZU minus ZL. This expression means that you are going to maximize lambda. Why we are doing or we are maximizing the lambda? Lambda equals to this value. What variable? It is variable. If we can dwindle or shortening the distance or the deviation of Z upper, we are going to maximize the lambda, and we are going to obtain the solution near the crisp value. Okay. So I can write the crisp model after converting the fuzzy to the crisp. As you see in this equation, I rewrite this equation. So Z minus ZL is greater than lambda ZU minus ZL, or lambda ZU minus ZL. Minus Z is less than negative Z lower. And in the general inequality or constraint, we can define other format for this inequality or constraint. And in the other format, in some books or literature and application of fuzzy in the linear programming, the researchers have applied the notation called P instead of ZU minus ZL. What's the P? The P is tolerance. The P is the allowable difference or deviation from main Z or Z upper. So instead of Z, we can use Cx. P lambda minus Cx is less than negative Z lower. And we can write instead of negative Z lower, ZU, ZL, Z minus ZU. What's the ZU minus ZL? P. What is the ZU? The main value. For example, in every constraint, we have the right hand value, right hand constant number is called, for example, D. This is general format of constraint for fuzzy linear programming. You can convert the structure of objective function to the constraint, and you can define the fuzzy structure for every constraint. And the general format is this that you see. Lambda multiplied to ZU minus ZL minus Z is less than negative ZL, or P lambda minus Cx is less than P minus D. This is other format or general format for all constraints, because we can convert the maximum or minimum objective function to the constraints. In the first place, we must know how we can write the objective function in format of maximum or minimum to the constraint. If you have maximum objective function, you can convert this to the inequality or constraint similar to this that you see. Cx is greater than Z. This is at least equals to Z. Okay. So after that, we can say that the maximum objective function is equivalent to Cx is greater than Z upper, or upper of the upper bound for Z. That previously we could say that this value is assumed that to be the optimum solution for the objective function. function. Then if we assume that P is equals to ZU minus ZL, you can rewrite this constraint lambda P minus Cx is less than P minus ZU. P minus ZU is P minus D. But we assume that D is constant in the general model, and for objective function, we assume that D is ZU. Okay? In this inequality, you can see Cx is greater than Zu, so you can convert this to other form with multiplication of negative in this inequality, and negative Cx is less than negative Zu. Then you can add the P on the right hand side and the lambda P on the left hand side. All these relations are related to the maximize or maximum objective function. Then I must explain the same relations about minimization or minimum objective